Thanks for inviting me for this talk. And I hope all of you are safe along with your families at this particular time. My name is Bharat, and I work as a GPU advocate at Nvidia. I'm basically a computer scientist and a parallel programmer, also AI enthusiast. AI is evolving at a pace, and one of the new and the most emerging workload of high performance computing or parallel computing. And also, I'm trained in for software architecture for non-functional requirements. So maybe this is a quick background about me, uh, but it's important to know where do I come from. Many of you might already know NVIDIA. NVIDIA is basically a platform or a computing platform company. Um, we basically started our journey with something called a GPUs, which is graphics processing unit. So far from the time it has launched, we have shipped more than 1 billion CUDA GPUs. If I talk it from a perspective of computing, it results into more than 250 exaflop of performance. Um, Almost all high performance computing and AI and data analytics workload are all GPU accelerated, and we'll talk about that into more details. And it has all become the reason for it is because of our architecture, which is called as CUDA, which stands for Compute Unified Device Architecture. NVIDIA being a company is not just about the hardware, but also the software stack behind it, which kind of powers the data analytics or the AI part of it. And we have more than 150 SDKs. The new era of AI is basically being defined at this point of time by the startups, because AI as a technology, it finds. Um, I would request all of you to be on mute. Can hear some noises. Thanks. Um, AI as a technology, it's not just about a technology, in fact, it's about changing the workflow, changing the business side of it as well. And that's why this is a time or the new revolution where you see maximum startups coming out at this point of time are based out on artificial intelligence, and it is touching no matter which field that you talk about. And all this is possible because of the developer base that we have. What is the agenda for today? I will quickly take you through some waves of AI. I think all the audience here know what AI is, what deep learning is, what analytics is, and the main thing is that we need to see what's changing in this field, and that's what I will cover in certain time. And I will talk about why what's this scientist time machine that I'm talking about, and why GPU plays a very important role there. Why there is a need for speed for all these applications that we are going to talk about. Things are changing a lot. Data is becoming more and more important, and without data, AI has very less impact. Technology like federated learning is playing a very important role there. We'll talk about some of this from our point of view, from the NVIDIA SDK's point of view, so that the SDKs that we give have already pre-trained networks there, and it basically helps you in making use of federated learning so that you don't need to share your data which is private or the fuel that you would like to have with yourself. We'll see some of these applications, use cases in different fields, including conversational AI like Jarvis, or smart cities like Metropolis, or Omniverse and Hyperion. We'll talk about that in more details. We'll also get into the details of how the architectures or the generation of computing itself is changing, and how does it make any sense from a point of view of quantum computing, and also how GPU is playing a role there, and what's changing in the ARM side. So one thing which has been established for sure is that accelerated computing is the path forward. Some of you might know this word, some of you might not. So accelerated computing, as the name states, it's about accelerating something. What are we accelerating? In case of high performance computing, I may be accelerating an algorithm called as fast Fourier transforms. Or in case of AI, I may be accelerating doing convolutions in the convolution neural network. Or in case of data science, I may be accelerating the pre-processing part or even the machine learning algorithm like clustering algorithm. Or what it can also do is that it can basically also accelerate some additional things. Accelerated computing is not something new. Things like your graphics, if you just look at it from a historical perspective, earlier days the graphics computing was done by the CPUs, and the CPUs were basically responsible not just for doing graphics, they were running the operating system and things like this. When graphics became really high definition and rendering became a problem, if the CPU was doing it, it basically resulted into taking away the clock cycles which it would have needed for running your operating system or applications like PowerPoint. Now, why did GPUs come into the picture? The name stands for graphics processing unit. And the reason why they were born was because we wanted to offload or accelerate graphics and offload it to the GPU, which is very good at doing that. And the same applies for data analytics. The same applies for many other fields, which we'll see. So it's not just you would see in isolation that there is something called as AI. You would not see that there is something called as networking. You would not see something called as robotics, but it may be a consolidation from a point of view of using the accelerated computing. AI has changed the way everything works. AI is a software that writes software, and it is becoming more and more complicated. It's writing more complicated softwares. It's trying to learn more complicated piece of patterns in your data with the data explosion happening. The new unit of computing is not just limited to one machine, it's the whole data center itself. There is no way today, if I need to be competitive in this market and do a lot of activities to be really applicable to the industry, I can make it just work on a single node or maybe with a single GPU. So data center itself has become a computing unit rather than talking about writing a code or using something in a single unit. And then it applies to different domains. There are new emerging domains while some of them have been existent. With 5G coming into the picture and the applicability of the compute which is going to emerge out of it, the number of subscribers which are going to be there by 2027 is humongous. The compute needs, the need for AI and 5G networking is changing the way networking is going to be done or the way the overall space will look like or the data centers would look like. Robotics is playing a very important role there. So there are different domains in which this is happening. But I'm not here to just talk about the domains. I'm going to talk you through the necessity of the speed that we talk about in this particular session. So in the AI space, I believe that most of us know there are newer and newer networks emerging. Convolution neural networks have been there for quite some time now. They are becoming more and more deep in nature. The number of parameters that you need to train is also increasing. There are new set of beasts which are emerging. When you have lesser amount of data and you would like to generate some artificial data, GANs have proven to be really, really useful. With more and more works being done in terms of natural language processing, other LSTMs have played an important role. Transformers have become really, really important with encoder and decoder. They have proven useful in many domains, and the level of complexity that they can handle at this point of time was unheard of. But at the same time, when we increase the complexity, so does the compute need, and so does the data need also increase with this. Reinforcement learning has already is being used, and it's quite popular in the agent space. Let me give you an overview of what do I mean by computing and what do I mean by networks or what do I mean by AI when I speak about the needs for speed. Nvidia released something called as Megatron. Basically, it trains something called as transformers. All of us know about transformers. It basically has an encoding engine and a decoding engine, and it is very popularly used in various domains. Megatron is a version which helps you in taking this large transform models like BERT and all, and it basically tries to train them parallelly across multiple nodes, across multiple GPUs. You can see at this point of time the explosion of the network that we are talking about to reach the accuracy levels or to reach the use cases that we want to do. 100 trillion parameters models by 2023, and it's not something that we are just saying, we are just plotting the trend which has been there. We are already at a stage of training up to 175 billion parameters at this point of time. And what we are talking about is training by 2023, the network is going to have parameters which are in the range of 100 trillions. Now, what does this mean for us? Basically, what you need is a supercomputer which can help you in training in this aspect. But can everybody have access to this supercomputer? Maybe not. So what happens in that particular case? What happens is that many of these parameters are already trained and they are basically kept in a, say, a zoo or a model repository of trained networks. And then what is provided to you is that you can take these trained networks which have been trained in such a large data set with 100 trillion parameters, and you can add your own complexity or your own data set to it and retrain it using transfer learning and also the federated learning which I told you, and use it. And that's what is becoming more and more important. And it's not just about the training. Training is one part of your overall AI flow. In order to make AI really applicable, it needs to be deployed in the real world. When I talk about deployment, there are different aspects which touch. Latency is one of the key parameter. If I search anything and if I get my result back after 1 hour, even if it gives me more accuracy, it may not be relevant for real world and it may not be of any use. If I create a model for autonomous driving and if I basically train it in a way that it only processes 1 frame per second for autonomous navigation, my car using that model is of no use. That's why you need to not just train it but also deploy it. So the solutions that you will see in the future will not just have the training part, but it needs to have an end-to-end deployment part also. Like if you were to do something you were to run the GPT-3 based chatbot, a one query usually takes around a minute on a dual socket CPU server. So if think about this, that you're using a chatbot and you get your request, you might lose out on your patience. With DGX 800, the same deployment, you can handle 16 queries within 1 second. And that's what makes it different. It's not just about the training, but inferencing an end-to-end solution, which changes everything. Why am I able to train it at that level, and why GPU computing? Which brings me to the part of heterogeneous computing or accelerated computing. I think I've already talked to you about this a bit, but let me just expand on this. GPU computing was born as a offload model, which means that there are certain parts which were being done by CPU. CPU, which is a general purpose processor which needs to run multitasking jobs. Like right now, I am running different aspects like a presentation. I'm also running Microsoft Teams and Microsoft Outlook and other terminals as well. These are all multitasking jobs. They need to run in parallel, and CPU is very good at doing that, and the operating system can schedule your multiple tasks really well. But many of the applications are basically of different nature, and they take a lot of humongous amount of time, like all your applications like data parallel applications. Like convolution neural networks, and when you're running it through the images or when you're doing graphics, you are basically traversing the pixels and you're trying to figure out a pattern and you're applying the same approach operations across. And those kinds of jobs are called data parallel jobs. And surprisingly, those data parallel jobs take a long amount of time. And they are the one which gets offloaded to GPU, while your operating system and other tasks still continues to run on CPU. And this model is called as heterogeneous computing, and which is becoming, or accelerated computing, which is becoming the new norm. When I talk about the new norm, I'm not just talking about CPU and GPU. We will see more complicated architectures in the near future for AI and other kinds of workloads, which I will show you, like security and all. Will not just have CPU or GPU, you will have units like DPUs, which are really good at processing your network data and trying to figure out different patterns inside it. So the world is becoming more heterogeneous in nature in this computing side. Every processor does its job which it's supposed to do. And that's what I call as accelerated computing in case of GPUs. Earlier, this acceleration happened for the graphics. Later on, it happened for your professional visualization and rendering. And then it got transformed into being used for high performance computing jobs like fast Fourier transforms, sorting or solving linear equations, and different kinds of other kinds of jobs in molecular dynamics on computational fluid dynamics. Why does it work? It may be represented in this kind of a cartoonish figure where you are seeing a CPU and a GPU. What you are seeing here is the difference, where you can see the GPU basically has large number of cores. They're different cores from the CPU. They are much more simplified in nature, but there are thousands of them. Like our Volta architecture has 5120 cores. As compared to your CPU, the CPU might have up to 128 cores, while GPUs has thousands of cores. You can practically launch 10,000s of threads on the GPU as compared to your CPU. While CPU can handle the multitasking jobs like which can fit in the CPU cores, well, that is 128 or 40 cores, whatever are present on the CPU very optimally, the GPUs can handle thousands of them very, very efficiently. If I were to do on the computer side to certain extent, uh, let me just put you in very simpler terms. Any processor that you buy has a silicon budget. It may has three main components. On the CPU side as well as on the GPU, I will say how do they dedicate it. ALU stands for arithmetic and logic unit, which is the actual computation or your core. Control is more of control of your flow of your application. You may have if and else statements inside, or you may be moving from one kind of application to another application. CPU basically, since it has doing a multitasking job, it does a lot of control unit. It also has a large amount of cache, but it dedicates lesser amount on the ALU. While GPU, as I said, it says that I will have simple cores but I will have thousands of them. And that's why it can do the data parallel jobs very, very efficiently. And that's where we see within the same silicon budget, GPU do a different job, CPU is very good at doing another kinds of job. And the combination together makes your overall application run faster. Now coming to the AI side of it, when I talk about AI, Nvidia AI consists of Nvidia as a GPU company, which I just told you. It's not just about the GPU or the hardware. Nvidia as a company has evolved, and a lot of amount of effort from Nvidia goes in not just the hardware, but also create these different SDKs so that the programmers can make use of those SDKs and work in their respective domains. And that's why GPU computing has penetrated every aspect of the AI space. The same had happened, and the GPUs became really popular because we export something called as CUDA. I'm going to take you through some of these SDKs and talk to you about the future of how it looks like. Some of them I might not be able to cover, but just to give you an idea, cuDNN is our library, which stands for CUDA-based deep neural networks. No matter which framework you use, which is TensorFlow, PyTorch, even MATLAB, and any other framework, Chainer, or whichever you use, basically behind the scenes have integrated our engineers have worked closely with the framework people to integrate this library called as cuDNN, which accelerates. As long as you have a GPU on the system, you would be able to make use of the GPU and accelerate your code to the next level. Similarly, in the data science space, we have a library called as Rapids. Rapids has various components. It has various equivalent libraries of your CPU. Like the most popular one in the machine learning space is scikit-learn. It runs on CPU. We have an equivalent library in Rapids called as cuML. cuML is an accelerated version of scikit-learn which can run many of your machine learning algorithms in parallel, and it can do it very fast. If you are doing any operations, IO operations or data frame related operations, cuDF and cuIO is library for you to read those data frames in a much more efficient manner. If you are doing graph analytics, there is a library from our side called as cuGraph. If you are doing deployment, TensorRT is a library which takes your model, optimize it for a deployment purpose. It will ask you for what is your target hardware, and based on the target hardware, it will optimize your network. And it will do other kinds of pruning and things like this to make your model much more compact so that it can be deployed. And below that is all the stack or the hard effort that we have put together in terms of making sure all these libraries are easily accessible across the different hardware stack that we have. So let me take you through some of them and give you a perspective. Why it's there, right? So why this is happening at this point of time? AI is becoming popular, as I said, because of its application, its usage, which we can have at this point of time. Why there are so many startups emerging at this time? Because you could apply AI and it being applicable at this moment of time. If I talk about G Healthcare, they are using it for accurately detecting diseases in 145 million hearts per year. If I talk about different trends, like you could get a personalized playlist for over 345 million listeners at this point of time. It's being used for finding out different trends across 300 billion pins using Pinterest. So the nature of the usage of AI at different level, it's just humongous, and the application is not just from a point of being cool, but also at the scale at which you can deploy it at this time. And when we talk about accelerated computing, what we are telling is that we are in fact giving you a time machine. When I say a time machine, what we are doing is that we are trying to accelerate your codes and giving you the compute power which is beyond Moore's law. Moore's law states that your number of transistors increases every 18 months, doubles every 18 months, and it can be directly proportional related to the performance. But with the data explosion and the kind of networks exploding, we can't just depend on 2x. We need much, much more than that power. And that's why we say that we create a time machine which can accelerate Moore's law and basically give you much more performance. And it's a full stack optimization. It's not just the hardware. Within a year from the time we released our hardware called as P100 to now being A100, you have seen 13x performance during a year from the time 2016 to 2021. The scaling has gone to the next level. You could scale at larger level. We are talking about doing 305 million atoms MD simulation. Now you might ask why I am saying this. I am saying this because it's not a molecular dynamics simulation from a high performance computing point of view, but it's a AI plus MD simulation. It's the largest AI simulation which has happened. AI is penetrating the traditional environments like computational fluid dynamics, molecular dynamics as well. So its application in this space of AI is touching every aspect. All the hardwares are getting changed from a 64-bit to the multi-precision environment, which you see here. Now let us switch the gears and let's talk about what is so fancy or what's changing in this space. What I'm showing you here is a Nvidia SDK or Nvidia platform called as Omniverse. Omniverse as a platform It provides you visualization and also collaboration opportunity, which means that designers or physicians, the physics scientists, and different people, the data scientists, could be sitting at different parts of the world and they could still collaborate with each other. They may be using different applications. Some of them might be using Adobe, some of them might be using 3D Max, some of them might be using Maya. And but it will create a virtual platform in a way that they could collaborate with each other sitting in different parts of the world. So it creates a portal for everyone to collaborate with each other. And it has its application not just in the world of visualization. As I said, it could be used for path tracing, it can be used for audio to face, and you can see different use cases of it being mentioned here. In this world of COVID, this is something that we are really proud to say, right? That people sitting in different parts where you cannot meet with each other, but still your productivity will definitely not go down. So maybe the video might not be so clear for some of you, being a webinar kind of environment, but nonetheless, I will play the video for you, and when you get the presentation, anyhow, you will get the gist of it. So I hope you got a gist of what I was talking about. The reason why I also brought out this is, think about an application which is basically autonomous driving cars. Autonomous driving car is one of the most challenging application of artificial intelligence at this point of time. One of the challenge of autonomous driving also is to prove that the models that you have created would work in different conditions. And these are some of the reality aspects that you can't do all those things in the real world by just deploying it on the car. What you need is a simulation environment. That simulation basically is a virtual environment where you would have different kinds of scenarios. You can create a foggy scenario, you can create a rainy scenario, you can create different kinds of signs, you can create different kinds of environments, different kinds of road conditions, and everything. Test it out in different millions of cases and then deploy it in the car. Now, this is what we call as drive digital twin. And this can be done in omniverse environment. Now, the collaboration can happen across these different aspects that I just talked about and make it much more realistic before it gets deployed in the real world. Now, that's the level of complexity, or that's the level of collaboration which is required. When we talk about autonomous driving, We can't just do it on the real world. We need to simulate it. And for simulation also, we need to visualize it and do the collaboration, which can be done in an omniverse kind of environment. So there are different applications, which one of the application I just told you, but there are different kinds of digital twins and different kinds of visualization which can be done before it gets deployed in the real world. One of the application of it is also robotics. With Isaac SDK that we have, you could do all different kinds of simulation with Isaac simulation, test it out, and then you could deploy it into the real world, into the robot, before even doing anything in the real world. So I just gave you an example of that. In fact, I just talked to you about this scenario of having a digital twin for Isaac, which is our SDK for robotics and doing different things on that side. So you obviously need a platform to do this. The platform that NVIDIA works on, obviously I just talked to you about the nature of this. NVIDIA DGX as a platform has evolved. You would see that it is being more and more, we call it as an AI supercomputer, and you can see out of the rankings that we have 9 out of the top 10 universities use it. Whether it is telcos, banks, consumer companies, US hospital, car makers, aerospace companies in various domains is what they use it for. But why am I calling it as a supercomputer? You could look at a solution called as DGX Station, and it provides you up to 2.5 petaflop. Now this is what I call it as a supercomputing at your desk. Now, it was earlier unheard of having a petaflop supercomputer sitting just next to you without making any noise, because it is liquid cooled and giving you the kind of performance for your training and the kind of inferencing needs that you have. So you basically have a supercomputer now at your desk, and that's one of the reason why AI has also become really popular. One of them is computing. The second one is obviously the data explosion, and the third and the third one is the availability of framework. So I just talked to you about all the three aspects that we are talking about. Now let's move to another angle. Measuring utilization of space is more critical than ever. It is becoming really, really important for looking at the utilization of space, no matter which domain that you talk about. If I talk about the COVID situation, where I will show you a use case, we are talking about seeing and making sure that there are not more than X amount of public which is there in a particular location, to make sure that the COVID spread is much more controlled. If I talk about traffic management, we are trying to do diversion of the traffics or change the way the signals would work based on where the traffic is coming from and at what particular point of time. The same goes with respect to retail or public safety, warehouse, stadiums, and access controls or transportation itself. And all this is really, really a big, big space. We are talking about it to be a 2 trillion industry at this point of time. The use cases are humongous. I will show you a use case here, which is a use case of social distancing. In India also, we had a hackathon which was conducted in collaboration with National Supercomputing Mission, where the whole objective of it was to figure out how many of them are not adhering to the norm of social distancing. And there were different products which were created using AI with that particular thing. But basically, if you see, it is a utilization problem or a proximity problem that you are seeing at here at this point of time. Let's look at another application. So now you might ask why I have been telling you this. I know that most of you are aware of this use case, especially in COVID time. There have been multiple companies which have got out in this space and have been trying to do this. Why I'm here to tell you is that the use case which I showed you is not just from a point of view of developing a model which could do face detection. It's much more than that. The applications requires different kinds, it goes through different stages. The first stage is the training phase. The training phase might require you to use pre-trained models, and you could use techniques like transfer learning to build and apply your own data to get better models. Then you need to create a pipeline. The pipeline is very, very important for you to create because the data may come from different sources. The data may be multi-model. It may not just be, say, when we were talking about a use case, we wanted to not just look at the videos of this person, but also we wanted to hear via the sound in case anybody is coughing. And with the intensity of that cough, we may also make a decision. So we are talking about a multi-model kind of environment, getting it from different kinds of sensors. So creating that optimized pipeline which could run this model optimally is another problem. Now, training can be done via your TensorFlow, PyTorch, or whatever model. You would need basically something which provides you this transfer learning capability. For building and creating this network, you need a different kind of environment like DeepStream, which helps you in creating a pipeline which is optimal for deployment. And then finally you deploy the model based on the necessity that you have. So this when I talk about application, again, I'm not just talking about creating a particular model, but to create an end-to-end model, for which we have a SDK which is called as Metropolis. You don't need to do any of these things. Basically, most of the networks pre-trained models are already present. There are defined pipeline, or you could create or add your own pipeline to this overall thing and make it deployable ready. What I'm using the word here is deployable ready. And then, yes, you have different solutions for different places. Like you could mitigate risk at entrance itself in case somebody is not wearing the mask, or if there is elevated body temperature, or if somebody is not following the line, or if there are problems like weapon detection in for the security part, or from if anybody is doing anything very different, like if somebody is having an action of hitting someone, right? So and before even that person hits, there will be a trigger which may sound. And things like social distancing and occupancy are one of the critical use cases which exist in this particular time. When I talk about hospital applications, it has reached to the next level at this point of time. Contactless control has become really important when you don't want doctors or the nurses to touch the patients. You need to make use of hand gestures or even speak to things like robots to make the things happen or provide the medicine to the respective patient. It requires much more deeper models at this point of time. And also, yes, patient monitoring, continuously monitoring the patient via videos and to see if there is anything anomaly which is happening, to see via surgery analytics on how the surgery is happening, to various other applications which can be done via the Metropolis thing. The same goes with retail applications. I'm not going to take a lot of time here on this particular part, but yeah, it's you basically the applications, all these applications can be easily deployed with the Metropolis stack. In fact, many of the smart city projects that are there given by government and all, many of them in fact are or may be using Metropolis in the future. The most challenging part at this point of time is related to conversational AI. India, having so many languages, having so many dialects, has the highest amount of challenges with respect to conversational AI. Currently, many of these AIs models that you see out there are being trained using English language, and then you hop over. So you train something, you convert it to English, and then from English you again convert it to some other language. There's a loss of accuracy which is happening at this point of time. One of the key problems also with this field is the availability of data. Now, there is certain amount which can be solved using an NVIDIA framework called as NVIDIA Tau, which makes use of federated learning, which I will talk to you about in certain time. But the state-of-art conversational AI stack from NVIDIA is called as Jarvis. Why is it important? I think I need not emphasize it in more. If I talk about telecom, we are talking about 2 billion hours of phone calls daily. If I talk about healthcare itself, especially in this time, we are talking about 30 million consultations happening daily. And many of them are not just written in just text or in form of writing, but also in form of audio. Many of us do not want to go to the hospitals at this point of time. There's a translation which is required. The content which gets generated obviously in the space of YouTube and all is humongous in nature. There's a need. The R is actually the need of the R is a framework which can solve this problem for us. So when I talk about this problem, it has not just one part. When I talk about the application, yes, you can create a model or you can have something working which may finally be able to work. Say, if I speak something, you may get a response after 1 minute. But that's not what is the demand of AI. Like, if I were to say which date the Chinese New Year is in, if I speak in English, the first part of this overall feature is ASR, right? This speech synthesis. You do a feature extraction, then you're going to create a caustic model, then you will be running a language model of it, and finally the decoding will happen. Then it goes to the NLU stack, where you will do a machine translation, you will do different things, you will do auto correction. There are different parts of models which are running in there itself. The output of that goes again back to speech synthesis and voice encoder, and then the audio comes out in Chinese. Now this is a very complicated model. It's a model zoo in itself. There are different kinds of model running, one providing input to the other, and in each in itself. Now the factor of complexity increases with the number of languages being added, with different dialects being added, and it becomes more and more complicated. It's the most toughest problem that the AI industry is solving at this point of time. And the solution for that from our side is NVIDIA Jarvis. We have pre-trained models up. You can see the number of hours which we have trained on multiple DGXs already present for you. What you can do is that you can download these pre-trained models which we have trained on, apply transfer learning, and basically or make use of federated learning using our framework called as Tau, apply your own data set, make it really applicable for the kind of dialect or the kind of language you want to add to, and without giving out the data. And then you can give it to Jarvis for doing the ASR, NLU, and TTS, which I just talked to you about. One of the key thing also is that when I'm talking about Jarvis, I'm talking about multi-model conversations. It's not just about taking one kind of input. It will take video, it will take in audio input as well, and it will do multi-speaker transcriptions. If you talk about our Rajya Sabha and all, think about this, that an ideal scenario would be that our PM speaks in, say, Hindi or Sanskrit, and it at the same time gets translated in real time to all the different kinds of languages that we talk about, and the other speakers can ask in their original language, in their own dialect, and the same gets transferred in the language which our PM can answer in. Now that's what we would like to have in the future. Now that's another aspect of the kinds of problems that we are solving in the space of NLP. Another most important aspects of AI and data science being used is in the security part. Every user workload of a data center is a security threat. One of the biggest problems which we can see, especially if you're using a cloud instance, and if you take a cloud instance which is given as a bare metal instance with sudo access to you, it becomes a nightmare for any cloud vendor to do it, to do anything with it. And that's what kind of problems that we are talking about. Nvidia talked about an SDK that we are releasing called as Morpheus. Morpheus is a solution which actually can do many things, and it can take decisions without even leaving that node, because now you could do real-time solutions within the DPU itself, or data processing unit, or the networking unit which is there inside that chip itself. And it is obviously based on the NVIDIA stack, but it can process your tokens. It can do intrusion detection in the future. It can also take security action, change the policies based on the kinds of packets. Like if somebody is watching YouTube and they're trying to watch something which they're not supposed to watch, if those kinds of packets are coming without even going to the firewall or without even going to the end and then changing the policy for that user, it can be done on the spot. You can change you can give an input security policies, and you can do real-time telemetry. And that's what is the change that we are looking at in the future from a perspective of usage of AI in these kinds of security applications in the future. When I talk about autonomous driving, and in fact, we are working with many institutes in India who are working on autonomous navigation systems, it's a very complicated problem. You can't have just a system which does certain kind of, I would say, detection of lane. Now, yes, you can improve accuracy at that level, but when I'm talking about at scale and the real world deployment, it starts from data collection and testing to mapping and training to doing simulations, which I gave you a perspective on, and then finally deploying it onto a car and also applying it to a virtual world. Now, all this is required for anyone to basically be successful, to say that they are basically being able to do something as a research in the space which has relevance for the industry or in the future. Now, this all comes as a package as different aspects. You have a simulation package, you do have a data collection and testing, you have a different thing requirement for training, a different requirement which is real time in nature on the driving side itself, and a different requirement for the navigation visualization part of it. Now all this comes as a tool from NVIDIA so that the researchers can work on end-to-end solution using the Drive platform. In fact, if you do have a car, there is a solution from NVIDIA which is called as Hyperion, which not just provides you the kit for which will do the processing, it also provides you a set of sensors like 8 cameras, 4 fisheye, 3 megapixel, 3 in-cabin, 9 radar, and two lidar. And it basically provides you, you can think of it like an architecture which you can put in your car so that you can do research on creating autonomous navigation car. It consists of data collection, development, and as well as testing. So it's an end-to-end solution or architecture for you to do research and change this industry as we speak, because this is one of the most the future is this, as well as the most I would say the compute heavy, and the research angle is very high in this field. Now again, I would like to highlight, no matter what I told you here, NVIDIA, what it has done is that it has trained many of these models which has trillions of parameters, and just trained them for you and put it on something called as NVIDIA GPU cloud, so that you can just go ahead and could start with these models even if you don't have such a large supercomputing facility with you. And then you can do a transfer learning of federated learning and do that additional aspect of making it better, do research on that particular specific data set, and do publications or do research in this field and also convert it into a product. So on NGC you will find production quality AI models where we have engineers or data factory who not just does annotations and all, and finally we release out all these models for you. And this is the framework which I just told you, which is called as Tau framework. Basically, it works on the concept of federated learning, where you could take an existing model which is already trained, protecting your data privacy. You could use this, train it using your own data set, and then maybe again make the model public itself without releasing the data. These all aspects are very important, not just from a production, but also to take the contribution of research forward, because not everybody will have access to such a large amount of data. It may be restricted to only the government, or with some special organizations or some special institutes who have somehow got access to, say, the healthcare data and all. And I would like to quickly summarize something from our perspective from ARM, which is the last part. What we are seeing is that generally the systems, the way they were designed was there was a CPU, there were up to 8 to 16 GPUs which were attached. GPUs were really, really powerful because they could do computations very fast. But if I were to see from a point of view of the data transfer happening between CPU and GPU was a big bottleneck, because they were making use of memory hierarchies like PCI for transferring the data. What you would see in the future is like NVIDIA introduced something called as Grace, which is a new computing architecture for AI and data science. Because obviously we do give you really fast compute. Along with that, we will also provide you really fast CPU. So the CPU is going to be ARM CPU, which is very popular, especially in this world of mobile computing, because it's very, very power efficient. Along with that, the problem of the memory to the GPU gets solved via this new architecture, which we call as Grace. And this is what we see is going to change a lot of things in the future, where you will have an integrated a CPU and GPU talking to each other with a very, very high speed memory bandwidth, and the transfer of the data, because in the traditional architectures that we have currently, it is not possible to do this, and your transfer becomes your main problem. And last but not the least, quantum computing, all of you would have heard of von Neumann architecture. As the computer scientists, we say there are things which we say that the new future of architecture or anything that you work on is quantum computing. But the good part is that even quantum computing research requires a lot of computing aspect and a lot of memory bandwidth. And with that, NVIDIA also provides GPUs which can accelerate your quantum computing in the future. When the quantum computers will come, we can accelerate the research of quantum computing from days to hours as well. I know we have exceeded the time, so I will stop my talk here. I hope it gave you a perspective in terms of what all use cases increases, and I hope I was able to emphasize enough on the aspect that it's not just about a computing which is in isolated fashion. It's about end-to-end computing, which is making the difference. With the explosion of data and the networks exploding, the necessity with respect to the frameworks and doing transfer learning, federated learning, and all those other things have also expanded. Before I look at the chat window, is there anything which the host would like to specifically would like me to answer?
Hi Bharat, this is Richa here. Pallavi had some internet troubles, so she is not online right now. Maybe she'll join
Okay.
shortly. In the meantime, thank you so much for giving such a wonderful talk. It was very informative, and we got to see so many different use cases that NVIDIA's systems are providing us mechanisms to handle. Right. So there are a few questions in the chat. So Sandeep is a PhD student in the computer science department. Sandeep is asking, is there any framework being developed specifically for AR VR applications?
Yes, there are AR and VR SDKs which we also have in this space, and unfortunately I didn't cover them, but there is a separate SDK for that, and you could make use of those SDKs for AR VR application. I don't remember the name exactly at this point of time, but I'll be happy to provide a reference to you later on. But one of the virtual reality application which I can tell you, which we started working on, was um, to how should I say, to preserve the national heritage that we have, right? So there have been, you would have seen different national heritage. You would see those videos where you could reproduce on how the ancient civilizations used to look like, how did the different old statues and everything used to look like, how were the houses used to look like in the earlier days and all. The same research is happening in India on the virtual reality part of it and AR part of it, where what they're trying to do is all our ancient sites are being trying to be converted into a virtual reality applications, and there are different startups working on it as well, who are able to do it. Primarily, it's a use case which comes from rendering and visualization itself. So GPU is definitely a good fit there, but it requires a different pipeline, and I didn't cover it here, but I will be happy to provide that reference later on to you. I see
Yeah.
another question on modern traffic problems using AI. So I gave you many examples on the traffic problem. In fact, when I was showing you, you can. So traffic problem is a multifaceted problem actually. It requires different aspects. It requires a smart city approach, where you need to do smart planning, which may take inputs from the cameras. It may take inputs from different aspects of the autonomous driving itself, or it may take different inputs from when do say the shops open, or when do the IT parks open at what particular point of time. So it's a very complicated problem, and as I told you, one of the solutions from our side there is obviously the Metropolis project. It is basically a project which is a project being used very heavily for creating different smart cities around the world, and it takes in different angles, as I said, different kinds of sensory inputs, converts it into a pipeline to make real-time decisions, divert the traffic, or do different kinds of or give insights to the before even it happens. It gives insight to the authorities that we see this which is forcing traffic coming in because of this pattern, and you should take some action on it. So the solution, what I can say at this point of time, is Metropolis, but it's a very complicated problem, and you need to have a very complicated pipeline there. There are different startups. There are many smart city projects being floated in India itself, Pune, Bangalore, and all of them have a different requirement with respect to traffic problems, and they're using it and stating it in a different way. So unfortunately, I don't have a very simple answer for you. Another question is how Grace will boost the quantum computers era. As I said, quantum computers will be there in the future, but you need simulation of quantum simulation before even quantum computers are built. Now, if you do quantum simulation and if you are in this field, you would realize that it is a very memory intensive part, and GPUs have a very high speed memory bandwidth, and also the compute is very high. So GPUs are proving to be really useful in quantum simulation, and the SDK that we have released there is called as cuQuantum, and it will help anybody who is doing research to create quantum computers to accelerate that simulation itself. With Grace, what happens is that now the memory bandwidth problem which is there currently also gets solved, so you will get an acceleration on that part as well. So in general, what I would say is that GPU computing is helping the next generation of supercomputers, which may be quantum supercomputers, by accelerating the simulation of quantum computers itself. Uh, in dependence on pre-trained model, this make big organization, Facebook, Google having supercomputing access in market controlling position where they may have their black box pre-trained models tweaked in some way to have benefit for their big funks. Now I can't talk for Facebook, Google and all at this point of time. I'm being part of enterprise. What I can say is that every enterprise have ethics which they adhere to, and they ideally they don't break any of these ethics. So Nvidia being a technology company, at least for us, it's very important that there is no hidden thing inside it for it. So if you don't want to use those pre-trained models, you're free not to use it in case you have some security aspects. And in fact, I did talk to you about security to a large extent, which is the biggest use case which exists at this point of time. Uh, is it dependent on billion parameters? Maybe or maybe not. You would be if you're following the research, there are very interesting research where with lesser amount of parameters and lesser amount of data itself, still the accuracy levels are at par with a model which was much more larger in size. So the researchers are also working in that direction, that you don't need to have billions of parameters and reduce it. But mind this, that it's not just about reducing that. At the same time, the data explosion and the parameter explosion is also happening. So there is a push where the researchers are reducing the parameters. At the same time, the use cases are also becoming complicated. So you may end up solving a not so critical or not so larger use case from a holistic point of view, but you may be able to solve a use case which may be good enough. In fact, in the autonomous driving car, we had an interesting hackathon which we did with Niti Aayog, and the team which won from IIT Madras was the one which didn't have a billion parameter for autonomous this thing, because they had a very simple use case. The use case was just to find out if the driver is sleeping or not. And for that, you don't need a very billion parameter problem, right? It was enough to have a very small model there and basically deploy it, because it solves your problem. Not everything requires billions of parameters, right? So it's still okay. And they won the competition, by the way. So I don't need to get into the grace. So you can read more on grace in the future. It's not something which exists at this point of time. It will be there in the future. So one thing is that obviously you will increase the number of qubits that you are doing the simulation on. The larger the number of qubits, the larger is the requirement on memory dependency. The larger the memory bandwidth and the compute which is provided to you, the better it is. So GPUs anyhow would solve it to a large extent.
Thanks, Bharat. Any other questions?
No, ma'am, that was a very great talk by Bharat sir. We really enjoyed it.
Thank you. Okay, if there are no other questions, then thank you so much, Bharat. Thank you for such an informative and wonderful talk. I'm sure everybody benefited and learned a lot. And thanks again.
Thanks, everyone. Thanks for listening and stay safe.
Thank you, everyone. Stay safe. Take care.
Thanks, ma'am.